Welcome, everybody. Good afternoon, and welcome to another session of our webinar series on data science and statistics. And today we have the pleasure of receiving Maurizio Vicchi. Maurizio does not really need an introduction, but nonetheless, Maurizio Vicchi is full professor of statistics at Sapienza University in Rome. He has, among other roles, he has been the founding president of the Federation of European National Statistical Societies, FENSTAT, head of Department of Statistical Sciences at Sapienza, president and secretary general of the Italian Statistical Society, president of the International Federation of Classification Societies, IFCS, chair of the of the European Statistical Advisory Committee of the European Union, representing the Council, and he is, as we all know, the editor-in-chief of the international journal Advances in Data Analysis and Classification. Mauricio is author of more than 150 papers on various topics as classification and clustering, multivariate methods, three-way analysis, and so on, published in highly ranked international journals. It's really an honor for us to receive Mauricio today, and will present us his recent work on factor analysis for modeling hierarchical latent concepts. Mauricio, thank you very much for having accepted our invitation. We look forward to hearing about your recent work, and the floor is yours.
Okay, Paola, thank you very much. Thank you very much, Paola and Maria Eduarda, for this very nice invitation. Thank you for the nice introduction. It is a pleasure for me to present, to have the occasion to present this paper. This is a joint paper with some PhD students and colleagues, Maria Bottazzi Schenone, Carlo Cavicchia and Giorgia Zaccaria, on the factor analysis model, and beyond the factor analysis model. We know that typically, and this gives me the opportunity to present this paper that has been just accepted in Psychometrica regarding the ultrametric factor analysis. Typically, when you use dimensionality reduction, what you do is to use classical techniques or more advanced classical like principal component analysis, factor analysis, or other techniques that usually produce a reduction into a set of non-observable variables that represent a reduced space. In my case, I'm going to take into consideration a situation a bit more complex, in which you have a space which has some specific characteristics, which is the ultrametric space, in which you have some space nested in some other subspaces, and you might have disjoint spaces into this ultrametric set of variables. So the idea is to introduce a new method to project the observations into a more complex space, but that allows you to get more information on the correlation that you have. So we start with the idea that we have a set of correlated, of course, variables, and we discuss this new methodology. So let me give you briefly a background, very short background, in order to take into consideration some ideas. We start with just the principal component analysis that we just know that is a orthogonal, linear orthogonal transformation, that maximize the variance of each component, each factor, each latent variable. I'm going to use these terms in a similar way because I will show you in a moment why. We have the idea that in the principal component analysis, you want to maximize the variance of the reduced space, reconstruct the reduced space, that reconstruct also the space, because principal component can be seen as a special case of factor analysis, the factor analysis, the exploratory factor analysis. Here on the right, you can see, just a second, that I want to move here. Okay, so you have just one factor model to reconstruct the variables, can be seen, the factor analysis and the principal components analysis. And indeed, the idea that the idea behind the use of the principal component analysis as a specific factor analysis model is given by this picture, in which you have the data that you want to reconstruct, and with PCA you are going to reconstruct, but with a special typology of error, isotropic error of the type sigma square identity matrix, while factor analysis can be seen as a more generalized methodology with respect to principal component analysis, in which you reconstruct the data again with some latent variables, so latent factors, but using a more specific covariance matrix for the error. In actually, what you in exploratory factor analysis seen as a methodology in which you use the structural equation model, so as a measurement model, you have that factor reconstruct all the variables, even if, as we know, that some variables are not reconstructing well. These dotted arrows do not reconstruct well the original variables. Some others do. And also we have the confirmatory factor analysis, in which you mix these two approaches, the approach to confirm one model. In the case of factor analysis, confirmatory factor analysis, you hypothesize because you think you have an idea, you have a theory that gives you the relations between the variable. You want to prove that this theory is actually confirmed. And so versus the exploratory factor analysis, in which you do not believe to know in advance the relations between variables. So the point is that in the case of confirmatory factor analysis, you go into a simplified representation of the relations between variables. You have this simple structure model in which each variable loads on a single factor. This is simplifies the interpretation because you do not have the cross loadings that typically make more difficult the interpretation of the results of the factorial methods. So the idea is to mix together some different hypotheses. From one part, you want to have a confirmatory method or an exploratory method according to the idea, if you know some information regarding the relations between variables or not. And then you want to have also a simplification of the interpretation of the results. So in this case, you have a completely confirmatory model in which you hypothesize some relations. In this case, the case B, you do have you have an exploratory situation in which you don't know the factors, and if you have even more levels of factors, not only the first order correlations, but also higher correlations. And higher order correlations. So the point is that typically in the exploratory factor analysis, you have this situation, but maybe what it is relevant to have one technique that you have mixed possibility to have some relation already fixed and some other not. So the idea is to develop techniques of this typology. And together with this, some colleagues from Gilbert Saporta from France and some other colleagues from Italy, we discussed this idea to have these joint techniques, not to have this simplified representation of the factors, just considering the idea that one factor is identified exactly by a subset of variables. And indeed, the disjoint principal component analysis and the disjoint factor analysis are two techniques in which you have start from the factor analysis model that you can see here from a matrix viewpoint, where matrix X is a centered matrix, Y is a set of factors, and A is the loading matrix. In the disjoint principal component analysis and disjoint factor analysis, you have a reparameterization of the matrix of the loadings into the product of two matrices, a matrix, a diagonal matrix B, and a row stochastic membership matrix V, which tells you each variable to which factor is belonging to, is explaining, is reflect the relations between factor and variable. So you have the usual typical hypothesis that you have in factor analysis model. We know that if Y is actually a linear combination and we estimate by maximum likelihood or also by least square using the just typical isotropic error, you obtain the disjoint principal component analysis. This is well known now because of probabilistic principal component can be obtained, its principal component that can be estimated by using maximum likelihood. And here we have the same situation. We can estimate by maximum likelihood the disjoint principal component of the disjoint factor analysis. Which are the hypotheses that are considered into these two disjoint techniques? The idea is that the correlation matrix that we see here is block diagonal. So there are high correlated variables, in this case 3 factors, that we can represent as in the case of a structural equation model that are going to reconstruct the original variables, and we hypothesize that no correlation is present between the blocks. So this is the situation in which this technique is going to work very well. but this is also the case in which the factor analysis and principal component analysis are going to work very well. When we have this situation of a block diagonal matrix, we see here, you can easily see that in this case, the observed correlation matrix 10 by 10 variables. This is a correlation matrix. What you have to you can explain is the total of the number of variables 10. And if you see there is no correlation between variables, and of course what you are going to explain is almost all the variance that is equal to 10 for the principal component analysis, and with the disjoint principal component analysis, you get just almost the same results as you can see here. And you can see from the loading matrix that in this case the components are disjoint already, are intrinsically disjoint from factor analysis and principal component analysis. Everything is almost zero. And disjoint factor analysis is just assigning each original variable to one of the components, or one of the factors, or one of the components in the case of the principal component analysis. As usual, you have that factor analysis explains less variance than principal component analysis, but as we know, explain better the correlation. And DFA is explaining almost the same quantity of the disjoint of the factor analysis. When problems are going to arise, to increase, problems are going to increase when we have cross-loadings. In the case of, this is a case of a cross-loading in which we have 3 blocks, clearly 3 blocks, but then you have some correlations between blocks. So you have the correlation between variable 1 and the variable of the block 3, 14, 60, 15 until 20. And also you have the correlation between variable 10 of the and the first block of variable 10 of the second block with the first block. In this case, you start to have a problem in the interpretation of the results that can be easily understood here. I have taken the same variance and covariance matrix. I have added some errors into this variance and covariance matrix, and you see that I'm going to increase some cross-loadings, some correlations. These are cross-loadings because represent the correlations between 2 blocks of variables, block 1 and block 3, okay? There are some relevant correlations that you can see move the, you remember that these 3 variables should be together into one single block, as it was in the previous case, but increasing the error, the quantity, the variable 3 is going to explain better another factor instead to describe the factor 3. And this is also what happened for the principal component analysis. In this joint factor analysis, this doesn't happen because, of course, this methodology is going to identify just specifically simple structure, so this still remain a simple structure in both in this situation. One might think that this is something that was happening in that example, but this is in a simulation study of the methodology of this joint factor analysis. So this is in the paper of this joint factor analysis, in which we see that we have some correlation matrices with 10 variables and 50 variables, in this case here, with low error. So here you do not have, you have almost zero correlation between variables, and then increase the error until to arrive to this situation in which the blocks are not anymore visible. So you see that if you compare this joint factor analysis with the other classical techniques to identify the blocks, to identify the factors, you see that using exploratory factor analysis plus Varimax, which is usually the default technique in factor analysis, or also using an oblique rotation method such as Promax, you still are going to get situations that are not so good as in the case of a disjoint technique. So you see that, of course, when the error is very, very high, almost is not possible to see the factors, you see that in this case, the adjusted RAND index that measure the ability to identify the blocks is going to decrease. This is actually is not the adjusted RAND index, is a percentage of correct classification. So now when it is necessary to explain something more, so in these cases in which you have some correlations between factors and it's difficult to explain the correlation, you need to introduce something different. So a higher order factor analysis. In the theory, we know already higher order factor analysis methodologies, which corresponds to apply factor analysis, then take the rotation, oblique rotation using, for example, Promax to obtain the first order factors, then measure the correlation between these factors because they are oblique, are not anymore orthogonal, so there might be some correlation. If this correlation exists, if there is no correlations, this means that the factors are intrinsically orthogonal. So we have these blocks of factors without correlation between the blocks. And so in that case, you have explained all the variants of the correlation that you have into your correlation matrix. But in the case in which you have some correlation, this must be factor, and you can use a second order. So what you typically do is you reapply factor analysis on the matrix of the first order factors in order to get some additional factors, of this time of the second order. Okay. So the idea is to go in this direction typically, but probably we can try to get better techniques with respect to the higher order factor analysis that I just explained, which is a sequential technique of factor analysis. So we want to get this hierarchical set of factors simultaneously and not sequentially, as in the case of sequential application of factorial methods. So this is to explain what I just said. If you apply to this correlation matrix, which is almost block diagonal, if you apply this joint factor analysis and this joint principal component analysis that you know do not need to rotate, no, because they disjoint factor analysis gives a unique solution up to a permutation, label switching of the factors, let's say, permutation of the factors. And in this case, you have just little correlation between factors. But in the case in which you have some cross-loadings, correlations between these variables, correlations between variables that are defined by cross-loadings, you get some correlation that needs to be explained. So this is the correlation between the three factors on which you could apply another factor analysis techniques. So we discussed this second order disjoint factor analysis, which is a technique to solve just simultaneously the second order. In which way? In this way that I show you. I start by considering two factorial models. The first one is to define the first order latent variables, the one that you see here, and with the usual constraint that the loading matrix is formed by a binary and row stochastic matrix, so a membership matrix, and a diagonal matrix that weights the relations. And then when we have defined a subset of factors, in this case 3 factors, we want to reconstruct these 3 factors because we believe that there is some correlation that has not been explained by one single factor G, which is the general factor that we want to get here, and a loading matrix vector C that tells you the weights that the relations between the general factor and the specific factor that you are going to take into consideration. In this case, you have that the variance and covariance matrix has this form here, which is the form of a factor analysis model, non-orthogonal, because you see that the sigma y is actually the correlation between factors, which has the form, as I said, of a unique factor CC prime plus the specificity of this single factor. So you can get the estimation of maximum likelihood, and in this case you obtain the solution. Then we extended this idea to the case to have a more hierarchical latent comp set, not more than 2 levels. In these 2 cases, you still have 2 levels, but you might imagine that in several situations, like in sustainable development goals, you have some development goals that are hierarchically organized into a form into subsets and are hierarchically defined. So the idea is actually to have one hierarchy in which on the top of the hierarchy you have the key comp set, the most, let's say, general latent variable, the more abstract in the sense. In a psychometric study could be the intelligence, no? Then you have some lower level general comp sets, less general, let's say, more going in the direction of representing variables that are in the bottom of the hierarchy. And so this then we have more specific concepts that are close to the observed variable. So the idea is now to have this dimensionality reduction, not anymore to get one single space, one reduction, but one, let's say, hierarchical space. And if you want a hierarchical space, there is a bijection that we know that we can have between a hierarchy of concepts, latent concept, and the ultrametric structure. Ultrametric structure that is a specific concept in this context, because, you know, ultrametricity means non-negativity of the if you are speaking of ultrametricity in dissimilarity data. But in our case, we have to include into the definition of an ultrametric covariance matrix, which are still positive semi-definite, also the hypothesis that the value can be negative. Here we have, just to show you, we have two papers, one of 2008, three papers, one of 2008, in which I have applied this for the similarity data. But then in 2020 and 2022, with Carlo Cavicchia and Giorgio Zaccaria, we have discussed the concept of ultrametric covariance matrix. Here you see that some examples. One example is this four blocks, 1, 2, 3, 4 block of variables, which are concordant. All the, let's say, blocks. So you see 1, 2, 3, 1, 2, 3 variables define one first factor. Then from 4 to 8, you get from 4 and 5, you have just one factor, and from 6 to 8, you have a second factors that then define a larger factor, including all the variable from 4 to 8. So here, this is a completely concordant set of concepts. In this case, you have two sub concepts which are concordant inside, but discordant between them. So you see that you move from the positive part of the relation between correlation between covariance, in this case between variable, to the negative part. Or you might have the situation in which you have a block diagonal in which you do not have any more correlation between, to explain between the blocks of variables. So now I am ready to introduce this ultrametric factor analysis. I think I have taken 35 minutes. Do still I have some another 15 minutes to continue to present? Maria Elena or Maria?
Yeah. It's okay. Thank you.
Ultrametric factor analysis, this technique that we just introduced, in which we have several factor analysis models that we are going to, let's say, simultaneously estimate. The first, each model is going to identify one layer of the hierarchical structure, one layer of the hierarchy, starting from the most correlated factors. In this case, you have 4 blocks, which are very highly correlated. So we start from 4 blocks, then we continue considering 3 blocks, 2 blocks, 1 block, no, at the end. So in general, these are starting from Q blocks. These are at the end 2 multiply Q minus 1 factors, no? A loading matrix of the size J, number of variable, and factors which are 2Q minus 1. This model is estimated according subject to the constraint that the matrix V is a membership matrix, so is binary and row stochastic. Here you see, and also considering the nested properties. No, that means that from Q to Q plus 1, you take just one let's say membership column that indicates the variable belonging to one factor, and you split this block of variables into two parts, just optimizing the estimation of the model. So at the end of the day, the variance and covariance matrix, the correlation matrix, has this form here, the form of several layers. I'm going to show you an example that is going to simplify this interpretation. A set of layers which are forming the correlation which are reconstructing the correlation between the original variables, starting from a block diagonal structure initially, estimated according to the first DFA, disjoint factor analysis layer, let's say, because we just estimate these 4 blocks here. And then we continue to estimate blocks to define the correlation between blocks. Okay. This can be seen as a classical factor analysis model. The ultrametric factor analysis, the UFA model, is actually a classical, more constrained factor analysis model, because you can rewrite the matrix, correlation matrix, as a prime plus a psi matrix, the specificity matrix corresponding to the error. And this matrix must have an ultrametric correlation form. So the idea is that we want to define the closest, let's say, ultrametric matrix to the original, ultrametric correlation matrix to the original correlation matrix, supposing classical hypothesis that you have in factor analysis, that the mean vector is equal to 0, the variance and covariance structure is A prime plus psi, which A has this form here, and we estimate the discrepancy, minimizing the discrepancy, as we usually do for the classical factor analysis model. Properties of this ultrametric factor analysis is it is scale invariant. It is scale invariant similarly to the factor analysis, but what it is interesting is that the solution is in this case unique up to a permutation. This is so because this comes from the disjoint factor analysis, which is indeed also define a unique solution. So let me show you this example to better understand what we are going to do. Let's suppose to have this correlation matrix. This has already almost a hierarchical structure, as you can see here, no? Because you see you have 4 blocks. Then these 4 blocks, you have 4 blocks are variable 7, 7, 8, these 2 variables, then variable 3, 4, 5, and 6, 3, 4, 5, and 6, this block here, and then you have a variable 1 and 2, this block here, and 9 and 10, 9 and 10, the last 2 variables. Then you get the relation between 7, 8, so you have this relation here that you have to estimate, okay? And then you continue in this way to estimate until you get then another block, larger block, in which you have to estimate these quantities here that still have to be explained by an additional level of the hierarchy, and then the final estimation of this relation here that connects the 9, 10 with the remaining block of variables. So this is the loading matrix. So it is 10 by 7. 7 is 2q, q is equal 4, so 2 by 4 minus 1 is 7 loadings, 7 factors, a matrix of 7 factors. The first 4 are disjoint, as you can see here, and you then have the second order estimation, the third order estimation, the fourth order estimation. If you apply just factor analysis, you are not able to, and you of course rotate by using Varimax as it is usually done, you do not get a solution which is comparable to the one that is really present in the data. So you cannot explain this complex characterization of the correlation matrix. And now I'm going to show you how this is computed. So we start from the most, let's say, correlated factors. Then, let's say, until the first 4th step, we have the estimation, no, of the 4 disjoint blocks of variable, the ones that you see here. Okay, so this is the correlation due to the first order factors. Then you estimate the second order factor, which is going to give some additional correlation to this block of variables that are going to get together. You see that before it was 0.44 almost everywhere. Now you get an additional part of the correlation due to what you have not explained according to the first order. Then you get an additional third order that you are going to estimate. And then at the end, you have the general estimation here of the general factor. You continue to estimate this at this moment. This is not a correlation matrix because you still have to define the specificity, and then you define the specificity as the difference between the diagonal of the matrix A prime and the diagonal of the original data, which is a vector of elements equal to 1. You see that the model is also quite with a reduced number of parameters, because for each within factor you have the same estimated correlation. As you can see here, you have this block of variable which have one, let's say, average estimation of the correlation, and also in these other two cases. And then also you have a sort of average correlation. So this parametrization is also very parsimonious, because you just have 2q minus 1 only different values to be estimated. And this is very good indeed in the case of a mixture model in which you want to estimate in a mixture model the variance and covariance matrix, taking in consideration just a few variables, just a few parameters to be estimated. We have shown this in one of the papers in which we have used this, let's say, structure, ultrametric structure. In our case, in this paper, what we do is to identify the loading matrix which is in connection with the ultrametricity of the factor analysis technique. The case of the block there, one might think, okay, but what happens if you do not have a hierarchical structure in the data? No, this is the case in which we do not have a hierarchical structure in the data. In this case, we know that factor analysis is perfect, also principal component, also disjoint, principal component of factor analysis identify perfectly. What happens if you compute the hierarchical, the ultrametric factor analysis? You still get a solution. In which you can see that no correlation is estimated between factors. So nothing really is not imposing. You are not imposing really a hierarchical structure. And here you see that these two links are almost connected. If they are perfectly connected, if they are at the same level, this is representing just one partition, the partition of the three blocks that we get here. We have one example, Holzinger as winner for the ability test. This is well-known data matrix in which you have a set of ability tests measured on 301 school children, and you see that a battery of tests has been submitted to the students, and we see that inside the battery there are some correlations that are have to be estimated, and indeed, if we apply the disjoint principle, the ultrametric factor analysis, which includes the disjoint factor analysis, we see that we get the blocks, but also we can estimate some correlations that were present in this part here and this part here. Okay, you see this is the ultrametric matrix which estimates the data matrix. This is the correlation matrix corresponding to some factors. And you see that you have additional information that you can explain with respect to the usual classical dimensionality reduction. So for factors, reduction of factor analysis, you still have the information regarding the blocks, but also you have some additional information on the relations between blocks and the correlations between blocks that have to be estimated. So with this, I finish my presentation. The paper is already present in Psychometrica, and you can download the paper into this journal. Thank you very much for your attention. Any question or comment is welcome, of course. Thank you so much.